Okay, yesterday we saw visualization and then the ideas of what is meant by plane, okay, rather than line. And you have to extend that to 100 dimensions. That's where I want you to think about that, okay?
Okay.
And also I introduced, it's not anymore, first of all, when in a multivariate case, we are talking about, let's say we are talking about, X, and let's see. I'm going to So what we are saying is, when we say multivariate, we are talking about X. Notation is sometimes like this. I'm sharing my screen. Okay, you're able to see this, right?
Yes, I can see that.
The variables are X1, X2, dot, 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 P, X, P. Right? We have introduced this notation before in linear regression. Okay, so we are not, and especially in unsupervised algorithm case, sometimes I'll write it shortly like this case. We don't have Y. Okay, we do not have. Remember that do not have the Y component, right? Which is what is called the dependent variable.
Dependent, yeah.
We don't have that. Okay, and I talked to you about variance, covariance of X vector because we have only now that's X, right? X dimensions. So sometimes we write it variance, covariance, variance like this, or variance, covariance, because it has a meaning, when you say covariance, because we don't have such concepts in univariate case, right? So we have some meaning like that. Also, sometimes it could be as simple as X. Okay?
Yep.
And we talked about what does this mean? This means in the case of, suppose it is 3 by 1, that is 3, P is 3. Suppose it is 3 by 1, then we talked about this situation, variance of x1, covariance of x1, comma x2, covariance of x1, comma x3. Are you with me?
Yep.
Covariance of x1, comma x3. And then I said it is symmetric, so I need to explain only this part, right?
Yep.
2x3, and then this is variance x3.
Yep.
Remember, variance x3 is same as standard deviation of x3 times standard deviation of x3, right? So when you divide that, this is what it is right now, right? I'm coming back. What is meant by correlation matrix? That is variance covariance matrix. What is meant by correlation matrix? You divide the rows and columns by the corresponding numbered standard deviation. Okay, so the first column is divided by sigma x1. Sigma x1 refers to standard deviation of x1, right? So let me write that again. One moment. One more time I'm going to do that. It's very important understanding and retaining this information. So correlation like variance covariance matrix. I can talk to you about correlation matrix, right? It's not anymore one, right? Correlation matrix is sometimes denoted as R. In the case of variance covariances, it is denoted as sigma, okay? Capital sigma. That is a capital sigma, okay? These are standard notation. So R is equal to, R is equal to variance of x1. I said divide by each row and each use, what is its position? It is where is x1 is first row, first column. So you have to divide it by the whole thing. We divide by sigma x1.
Sigma of x1, sigma of
but this will
x1.
be covariance of x1, x2. It is divided by sigma x1, the first column, but it's the second row, right? So it should be sigma x2. Are you with me?
Yeah.
And like this here, covariance of x1, x3 divided by sigma x1, sigma x3. Agreed? By first column, first, and then your corresponding. So, probably no. If you are a row-oriented person, you will put the notation first for the row and the sigma for the column next. But don't do that because again it is symmetric, right? You put it.
Yeah.
So here, so it is symmetric. So that's what happens here. Covariance of x1, x2 here, right? Stay
Yeah.
here. Sigma
Sigma of x2, x1.
x2, x1 or x1, x2, you can put that. Okay, that's
Yeah.
fine. Sigma x2, sigma x1. Here it is variance of
Variance.
2 divided
x2.
by sigma x2, sigma
x2.
x, right?
Yeah.
And then here covariance of x1, x3, x2, right? x2, x3. Sigma covariance of x2, x3, correct? So accordingly, sigma x2, sigma x3. Are you with me?
Yeah. Yeah.
And finally, this column is covariance. Can you tell me what they are? I would like to write it just now.
Yeah. The covariance of
Covariance of
x1,
right?
x3 by sigma of x1 and x3.
And it is very easy to think. Just put this number. That's all, really, right?
Yeah. Corresponding to that. And that is covariance of x2, x3 by sigma x2, x3.
Excellent.
The
That's
last
it.
one is the variance of x3 by sigma of x3, x3.
X3. Okay. But if you look at it, this is 1, right? These diagonal elements are all 1, isn't it?
Yeah.
So that's why the corresponding notation we use here is, let me do one thing. I need to move this to. Okay. So R, the way we write R is, this is the notation we have, R12, R13. This is what it means.
Yeah.
That's correlation. This one is correlation of 1 and 2, right?
Yeah.
R1, 2. That's the rotation we use. This is, I don't have to say that again, symmetric, right? This is 1, this is 1, this is R2, 3. Are you with me?
Yes.
This is symmetric. Remember that.
Yeah.
Both, let's write it. Both sigma and R are symmetric matrices. Okay? Both are symmetric matrices. Not only that, okay? The sigma matrix, okay, I'll write. You are getting comfortable with the mathematics and all, right? It's not difficult, okay? Just 3 times you tell, if you come to, that's it. The sigma matrix is sigma matrix, that's the variance covariance matrix, right?
Yeah.
It is positive, positive definite, not similar, positive definite. Variance can be 0. That's also 0. Then it is positive. Any diagonal element is 0, then it is positive semi-definite. Okay? Possibly, but very rarely, right? Semi-definite. That means in the mathematics, what it says that if you take any real numbers, the numbers, right? Usual numbers. If you take any vector, I'm going to simply write it like this. I don't want to put x. I'm going to put, let's say a1, a2. You pre-multiply and post-multiply by that, then it will be a positive number. That's what it means, okay? a1, a2. Okay. I don't have to detail it. In detail, I have to write. I don't have to write it. Are you with me? Is a number, positive number. That's what positive definite means, okay? But, in advanced concepts, what we are saying is that all the eigenvalues all is of sigma are positive. That's what it means. Okay? So far, so good? This is the
I
same
think
thing.
maybe I missed that. Why it has to be positive all the time? Can you
No, it's
explain?
variance. Remember that? Single variable variance. Thank you. That's, I should have said. Single variable variance. Is it positive or negative? It's always sum of squares of differences, right?
Yeah,
Between
yeah.
value and mean.
Correct. Yeah,
So
it
it
is
has to
positive.
be always positive. It can be zero, but if it is zero, it's not a statistical quantity at all.
Yeah, correct.
So it's always positive, right? Remember that?
Yeah.
But the problem is, yeah, I'm fine with that positive quantity, but what happens when I have like this? When I have like this, can we say this has to be positive? No. Covariance can be no, negative also.
Yes.
Any one of these can be negative, but these have to be positive.
Yeah.
Okay? But then I'm confused. So the variance, each individual variance is positive, but together joint covariance. That means the whole matrix. Can we say anything about positive? That's what this positive definite means. Good?
Okay.
So, but the other thing is now you can say the same thing like this, right? You can say the same thing like this. All eigenvalues of sigma have to be positive.
Mm-hmm.
Similarly, we have the R, but in the case of R, we don't say that. That's where I'm going also, right? In the case of R, we don't say that it is positive definite because it can be negative also. In fact, individual, um, um, we know that the individual pairwise correlation coefficients can range between -1 and +1. We know that.
Yeah.
Okay, so we don't say anything about that. So far, so good, right? And
Yeah.
this is where I know it becomes important for us. This is where eigenvalues and eigenvalues become important. Then what is the eigenvalues? Then I'm going to go over eigenvalues and eigenvectors. Okay, eigenvalues and eigenvectors become important to us. Okay. So and then I said, eigenvalues and eigenvectors are new eigenvectors are new coordinate systems. Why do I go to coordinate systems? Okay, because in the 3-dimension, you just take the 3-dimension. Okay, this is x. Are you with me?
Yeah.
And this is z. It is projecting towards us. These are negative directions are all, and I am putting it as dot. So this is not negative. I need to keep something as positive, right, on that side also. Are you with me?
Yeah.
So this is a coordinate system actually. This is the coordinate system, and here if you have 1, 2, 3, and so on, you have 1, 2, 3, 4, and likewise I have here 1, 2, 3, 4, isn't it? It's a negative, so let me go in that side. 1, 2, 3, and so on. Right? It's a coordinate system. That means what does it mean? Every point has 3 reference points on each axis. That's what a coordinate system. But what we are saying is that the eigenvalues, because rotation, skewing, scaling, okay, reflection, all these things are important. We want to have an algebraically possible way of discussing that without getting into pure computation and the geometry, the visualization. Algebraically, we want to have a system, and that's where what we are saying is the question that we are answering in eigenvalue system is there can I create a new coordinate system which is a combination of these xyz's? Okay, the question we answer in eigenvalue. The question we try to answer in the concepts, in the definitions like eigenvalues and eigen system is the following. Can I find a new coordinate system that is a combination, yeah,
Yeah.
of XYZ. That, and it has, remember, matrices are always about linear systems, linear systems. So basically, I'm saying, can I find a new coordinate system? So basically, rotating this, if I rotate this, let's say something like this, for example, I rotate up to this, let's say, then this becomes new coordinate, right? Like this. Do you understand what I'm saying?
I mean, the coordinate system is moved now, right? By a certain
I can
angle.
move also, but I can just simple case of rotation. You can move, you can do all kinds of things. Shift the location
Yeah.
or keep the location, but just rotate it. Shift the location and rotate it. You can do all those things in any axis, right? But
Yeah.
but it is creating a new coordinate system. That's what. But we want that coordinate system to be written in terms of the original XYZ. That is what we are talking about, right?
Okay.
And
Okay.
and the way to find that out is the following. What is going on? Even though we are talking about the coordinate system, we want to talk about the coordinate system with respect to the matrix, which is referring to some kind of a transformation, which is referring to some kind of a translation, rotation, scaling, reflection, all those things. Okay, so we are talking about, can I find a new coordinate system that is a combination of XYZ in relation to the matrix that we have on hand.
Okay.
Okay, so we are not talking about just randomly trying to find a coordinate system. We have some matrix through some mathematical process. Okay, and for that matrix we want to find out the new coordinates. Are you with me? That's very, very important. And what we are saying is that, this is very easy. What we are saying is that we just solve this problem. That is, for any vector and the given matrix, okay, the given matrix, for any vector, if you apply that vector, AX, that is a transformation, remember that, okay? Matrix calculation is the transformation, right? You apply.
Here is the matrix, right? And X is a vector.
Go ahead.
A represents the matrix and X represents the vector, right? Yes.
It's some vector which we want to determine what that is. Okay.
Yeah.
So it is not going to be very, again, given a matrix, it's not going to be, we are trying to find out just randomly some coordinate system. We are very specific to some coordinate system. Okay. What we want is, if you apply the transformation, it is just a scalar. That means a number. Scalar. That means a number. Okay. Scalar multiplication of the x-axis, x vector. So whatever the multiplication you do, multiplication is the transformation we are talking about. A transformation is a multiplication. You saw that in the previous notes I showed you, right? All the reflection, expansion, location shift, and scaling, skewing, all those things are just matrix transformation, multiplication. So what we are saying is, when we do a multiplication like this, we want a special system where it is just multiplying, the transforming AX, transformation, which is multiplication, AX, is just a scaled version of the X vector.
Okay. In a different coordinate system.
Because I am coming there. What is the coordinates we are going to come? Those coordinates are going to be defined not by x1, x2, x3 or xyz, but the whole vector is not okay. In this coordinate system, let me finish this part. I think I should go back and say that too. I should have said it. In this coordinate system, okay, in this coordinate system on the left, these are the 1, 0, 0. 0, 1, 0, 0, 0, 1. These are the coordinate vectors that defines your points there.
XYZ.
Right? But here it is going to define something. X1, X2, X3. Okay, this is let's say X11, X12, X13. Are you with me? Because there are going to be like this one. This is X. This is Y. And this is here also going to be three of them, right? That is X1. Let me do one more thing. I have to move this. I want to move it here. Okay, I need space. So there is another axis vector. Remember, a vector means vector is pointing is defining direction. Okay, and the length, right? You know that as an engineer, direction and length defines a direction. The vector defines direction and length. Okay, and this length is each other 1 unit. You remember that? Just 1, 1, 1, right? 1 unit. Length is what? Length of a vector is square root of the first element, right? X1 square, X2 square,
Second
X1
element, third element square.
X13 square. That is the length. The direction is, this is the direction we're talking about. Do you see what I'm talking? Right? This one. X is equals to this direction. Okay? And the length is, because X11 is 1, X12 is 0, 0, it is just 1.
1.
Okay.
1 for all the
the direction for the first one. Second one, this is the direction. Third one, this is the direction. This is the direction. Okay, positive. If I say positive, on negative side also. So in the same way here, we are talking about X2 vector is X21, X22, X23. Let me finish this part, and I will say something very, very important. X31, X32, X33. So these things don't have to be zeros or ones. It can be any fraction number also. Are you with me?
Yeah. So
that is the mathematics part of it. That will give us, that will derive, take us to the derivation and solution. I will finish this part. Very, very important. I need to finish this one. What is this? AX. Let me rewrite that once again. AX. I'm sorry. Okay. AX equal to lambda x, right?
Yeah.
Same as writing. Okay. Same as writing like this. Same as writing as A minus lambda I times x equal to 0. Why? Because this I can write it as lambda ix. I is the identity matrix. Okay?
Yeah.
I is identity matrix.
Yeah.
Okay. So basically this is equal to 0 happens if A minus lambda I determinant. This is the definition of determinant. Means determinant. Okay? Equal to 0. This particular structure has to become 0. Then only the solution exists. Okay, this structure. For that, 0 equal to 0 can happen when determinant is 0. Don't worry from now on. Okay. Now we just we are not going to worry about all these things. How we get all those, the eigenvalues and eigenvector. We basically solve the equation. Basically solve this equation. That's all. Are you with me?
Yeah, just that this holds good if the determinant equals to 0, right? But
yeah, don't worry about it. I think I just want to say that point. Maybe I shouldn't even need to say it at this time. I'll come back to this one. Just how to solve this equation. So here we know A. We don't know what we don't know is lambda. We don't know x. Okay. So that's where the determinant comes now. We don't know x also. We are not talking. We don't know x. We know that in equation. That's what in equation solving an equation means, right? So solve for lambda and x in this linear equations. Are you with me?
Yeah.
Super. You don't have to worry about that. You're solving, you don't have to worry about it. Just go and do it in R. So let's have a little fun in R. Okay? Are you with me?
Yeah.
Good. So let's go to the system. I'm going to share now. R. Okay, you're seeing my computer now.
PowerPoint. In your PowerPoint.
Now, what do you think so far? I think today I'm really happy that we went through nicely, systematically, how all these things are connected. Eventually, I come down to some solving equations as a way of reconstructing the coordinate system. Okay, reconstructing the coordinate system. Right? That reconstruction of the coordinate system refers to basically solving some linear equations. One extra problem is that I got lambda also there. X we always solve. I got now lambda also. That's the only extra problem. Are you with me?
Yeah.
Okay, so far so good, right?
Yeah.
And I said, at the end, I said, you don't even have to worry about it. From now on, you just go and apply the R to get us the eigenvalues and eigensystem. So let me complete this one. A transformation, which means any number of things. Scaling, reflection, queuing, all those things.
Mm-hmm.
Rotation, all those things are essentially captured by a matrix. First sentence. Second sentence is, given that matrix, in order to make our understanding more precise, more valuable, given that matrix, we want to find out a new coordinate system. In that new coordinate system, that rotation, that scaling, that reflection, that skewing, everything is basically, I can find those points with respect to a new coordinate system. Okay? Mm-hmm. Interesting. And then the new coordinate system, should have all those points only a fraction or a scaling of that vectors, directions, coordinate system directions, new coordinate system direction. And that new coordinate system is what is called the Eigen system.
Okay.
So we need two things there. One is the directions of the new coordinate system, which is called the eigenvectors. The other one is the scaling. So sometimes we may have to scale that differently than what we did. That's what the lambda is all about.
So when you scale, when you're saying scaling, what are the lambda attributes? That's the lambda. Okay.
That's a lambda. Scaling means I'm talking about here lambda. But forget about that scaling there in the transformation. This is now that the axis all has to be given what that scale is. Here the square scale is 1 unit. We know that, but that may not be exactly there. So we allow that variation to happen. That's what the point is. And given that, okay, now we are ready to use R and get those eigenvalues, because we don't want to get into the rest of the system because we know how to solve the linear equation. We don't have to get into it.
Yeah, but we know X, we know, we just need to find out the lambda, right?
Extra. We know it is basically, remember, it's a linear equation. A minus lambda I x is equal to 0. It's a linear equation. This linear equation, we always know how to solve. We have one extra number, that is the lambda.
Yeah.
So if you have, basically it's a linear equations, extra one thing is that's lambda to solve for. Okay, that's okay. What I want to bring here, Patro's question yesterday, he said, oh, you know what? We don't know. Sometimes, the equations may be different He didn't say that word, but equation may be dependent. That means one can be a multiplication of other, or one can be a multiplication of something else and subtracted with another equation. That you remember what is row operation? When you do that, then the whole equation, whole row will become zero. In the row transformation approach, when you do that, the whole row can become zero. That means, even if you have 3 variables, there could only be, inherently only 2 variables. Okay? What are we going to do? And that means their inverse doesn't exist, technically speaking. Right? Inverse doesn't exist. But there is a way to do that. That's not a problem. And, we call it as generalized inverse, which basically has to take care of the dependency of the observations. Don't worry about it, how the mathematicians do it and so on. We don't care about it. What we care now from on is that we want to get into how to find out this new coordinate system, which is a new Eigen system, new coordinate system, which is called the Eigen system for a given matrix, and work with that. Mathematicians did one more thing. They made the coordinate system in such a way that, oh, by the way, I have to tell you, let me tell you. So I said, let me finish that part, very important, right? So I showed you that Eigen's system involves lambda values. Let me go back to this. I'm going to go back to this board. Let me explain that one more time. Okay. So what I was saying is, okay. So you got the screen now. Okay. So what we want to conclude here is the following. I said A x equal to lambda x, right? This gives a new coordinate system, and lambda is the scaling number in the coordinate system, right?
Yeah.
The new coordinate system, right? But what I should have very clearly made that point also. So we said, it's a new coordinate system, which is a function of like this, right? This one, right? This one, and this, right? Which is a combination of x1, all these numbers, which doesn't have to be, none of them needs to be zero. And here, this is the beautiful, on the leftmost corner I'm talking about. It's a beautiful simplified system, isn't it? This is a beautiful simplified system, right?
Or the base system, right? From where we,
right? But
derive.
Here, the unit of length is 1.
1, yeah.
But here, what we are saying is unit of length is not 1, but it's lambda 1, lambda 2, lambda 3. There are 3 scaling parameters, lambda 1, lambda 2, lambda 3. There are 3 coordinates. There is x1 coordinate, x2 coordinate, x3. This x1 is different. This x is different from this x1. I remember that. Okay. Are you with me now?
Yeah.
So
yeah.
this equation will give us 3 lambdas. We are talking about actually, 3 lambdas to estimate in addition to the corresponding x vector values. Okay. So is resulting into 3, in the case of 3 by 3, right? This is a 3 by 3, remember. This matrix, for example, so far I have been working on 3 by 3, isn't it? So this has to be 3 by 1. This has to be 3 by 1. This is 1, remember, right? 1 number, just one scale, 1 number, right? That's what the lambda is. So the result in the end is there are 3 lambdas and their corresponding three lambdas, which are called eigenvalues, right? They're called eigenvalues and corresponding eigenvectors, 3 eigenvectors. Are you with me? 3 Eigen. So this is whatever the solution we are going to find out involves all those things. Okay, we find first lambda and then corresponding one solution with a vector value, right? Once you know the lambda, then you get the x vector, right? Because it's an equation, and then you find the second, you find the third, and you can find 3 maximum. Okay. If it is a positive definite matrix. If it is positive semi-definite, that means at least one of the variance is 0, then it will be less than 3 lambdas. Okay, now so far so good.
Yeah.
Only thing is we want to see some. Okay.
Yeah.
So let's come back again here. R action. So you're saying, let me go there. And then that's where I started, showing you this, take these examples and then do the work. Let's see what happens, okay? We can do any one of these matrices now, right? We just have to apply this equation. I can find out what is this new, is there a new coordinate system where I can use I can find that new coordinate system, which is a new Eigen system, okay? Which is an Eigen system, okay? So let me go back to this example. I think I worked out this example. Okay, this is the one I was talking about, right? Remember? Are you with me? 2, -1, -1, and 5. There is no lambda. Just I'm talking about the original matrix 2, -1, -1, 5, right? And then if I want to solve this problem, determinant is equal to 0. It is easy. Determinant is cross product, minus of this cross product, which is what this one is, equal to 0, which is basically a quadratic equation. Are you able to understand what I'm saying so far? This determinant, I'm going to do the hand calculation and then I'm going to show it to you in R. Are you with me? Are you able to hear me, read? I can't hear you.
Sorry, I'm on mute. Why are you subtracting with lambda? 2 minus
because
lambda.
you want to solve that problem, you remember? A x minus equal to lambda x means A minus lambda I.
Yes, yeah.
Times x equal to 0. And then I said the determinant should be equal to 0 for that solution to exist.
Yeah, okay.
Okay. So, that's what this A minus lambda I is this. Lambda I means only corners are minus lambda. That is not, it's not going to affect off time.
Okay.
So this is A minus lambda I.
Got you. Yeah.
Now and then determinant should be equal to 0. So determinant, for a 2 by 2, you know how to do it. Very simple. You don't have to use adjoint method, all this. So this times this minus of this times this. That's what this is. 2 minus lambda times 5 minus lambda minus 1 equals 0. And I simplified it like this. Are you with me?
Yes, yeah.
And it's a quadratic equation. The quadratic equation is the solution is on the right side. Formula. And I apply that, I get this value to be like this. Okay.
So the lambda is 5.3 or 1.7 for this.
Yes, exactly.
For this, coordinates.
Yes. Now I take this one at a time. I take this one at a time. Put this in this matrix and then solve for the equation for x1 and x2. And when I put that the 1.7, for example, this is what the matrix I get. And you know how to solve this problem.
Yeah.
Once I know the lambda, you know how to solve the problem. So I can get this solution here, and that will be x1, x2 will be your first eigenvector that corresponds, not first, in this case second actually, as an example. The second eigenvalue is 1.5, 1.7. So the corresponding eigenvector is what the solution of this equation is. Are you with me?
Can you repeat that again? The last
one. So as an example, I took 1.7.
Oh, okay. Yeah.
I applied that here, and this is it. This becomes like that. This becomes like this.
We're substituting lambda is 1.7. Yes.
times the X vector. This is a, it's a new A
Yes.
matrix. Let's say, A prime, not A prime. Let's call this as B. B times X equal to 0. That, you know how to solve this problem. It's an equation, right?
Yes,
Again.
correct.
And you solve that, what will you get? You get value for X1 and X2. That is your first eigenvector.
Yeah.
Okay. So let's just do the same thing in R and let's see what that eigenvector is, okay?
Yeah, sure.
Okay, so I do this. Okay, I'm going to do that here. Let's define it A. I don't know, wait, okay. A is there or already? I don't know. There is nothing there. Okay, so let's define A is equal to, how do you define matrix? Okay. C of the vector values I give.
2 minus 1, 2 comma minus.
Minus 1, comma, minus 1, 3. Okay. And then by row.
Yeah, it is 2, right? Is it not? Oh, yeah, it is, right?
What is that? What is it?
2 minus 1 minus 1, 5. Is that not?
Oh, 2 minus 1.7, right? Is that what you're saying? So it's not, it is.
Oh, okay. No. You are right. So.
Yeah. 2, it is approximated grossly. That's what you're saying. Okay,
Yes,
so
yeah.
0.3, right? 0.3. Second one is minus 1, comma, 1.3. Are you with me? No, not 1.3.
No.
3.3, right? 3.3.
No, I think I completely missed out. So initially I was saying the original matrix is 2 minus 1 minus 1, 5 before we transformed it, right?
Oh, yeah. I can go as per the original matrix as eigenvectors, or I can say solutions for this.
Oh, okay. So, okay, got you. So you are doing for this
Same
then,
thing.
yeah.
Good point. Same thing, okay? Good point. And nonetheless, it's a very, very interesting point to think about, right? The way you said it, right? So this is what it is, right? By row is equal to true, right? By row. I think we have to say by row. I don't know why it didn't come, but let's see. Okay, and then by row is equal to 2. And then I have to say n row is equal to 2. Okay. Oh, what is it? It's not matrix. Okay. So if I do this, A is this. Are you with me?
Yes.
But I don't need to do this. Let me go to the other one, as you said. Okay.
Yeah, after substitution.
After substitution. Okay. But for this, I have to find out the solution. But let me go back to the other one you said. Okay. That's also fine. So I'm going to call that as a matrix B. Okay. In fact, that's what we need to show, right?
Yeah.
2, comma, minus 1, comma, minus 1, comma, 5. This is what we want to show. What is its eigenvalue, right?
Yeah.
By row 2 and n row is equal to 2. So the command is very simple. Eigen B, that's all. And what did it do? Look at this. Eigenvalue is 5.3. Another eigenvalue is 1.7, right? And
these are the lambdas, right?
These are the lambdas. And first eigenvalue has this first eigenvector. Second eigenvalue has second eigenvector here. It just so happens it is, it's not really symmetric though, because here minus and here it's plus. Remember that, okay?
Yeah.
So your first eigenvector. So what is the first eigenvector? That is this is the new coordinate system. That direction is determined by these values. Minus 0.2897841. Okay. That's the first eigenvector. I mean, there are two elements that should be there, right? Because it's a two-dimensional problem. So the next value is 0.957092. That's your first eigenvector. The corresponding eigenvector.
Yeah.
So for the second eigenvector, what is that? The first value is minus point. This one minus
957. 95709.
Second value of the vector is this one. Okay. So far so good.
Yeah.
Okay. Very interesting.
Okay.
The diagonal values are same. That's very interesting, right? Half diagonal values are negatively changed. Okay. Now, this is how you would find. You just use this kind of command. Again. Okay.
Yeah. Can we derive this the step that we substituted the lambda?
No, I can do that. I have to use the solution command. So I have to go back to. We can do that. That's not fine. That's fine. For you to get the comfort level. And I would ideally would leave it to you to use R and convince yourself.
Okay. Because that should be the same, right? Should return the same as well.
Yeah. The command you have to, absolutely. The command you have to use is R command for solving equations. Okay.
Okay.
You have to find out what that is. I think it's called solve. So why don't we do that? We'll do that. Okay. So AX equal to, let's do that. So I have to give A value and B value. Okay. Then only it will solve. So let's do it. It's fine. Solve. Okay. So I need to know solve command refers to the following. Okay. Solve A comma B. You have to say that. Are you with me?
Yeah.
And you know what is A is. In this case, it so happened I called it as B. Okay. And C will be your 0, 0. Okay. So what is not B? I'm sorry. B is your original matrix. A is your solve the substituted value matrix. Okay. So fine. Okay. So let's solve that one. Okay. Solve. We know A, right? A is the one we are trying to solve, isn't it? That is, this matrix is A. Remember that.
Yeah.
And C is just put 0, 0. It should work. Let's see. Okay, I'm going to put it as C like this. There you go. Right? What is going on? Solve A. Let's call this way first. Okay. C is equal to 0, 0. Now I say solve A, C. What is it? What's going on here? So we applied this. This is what this one is, right? And I apply it 2 minus. That is a trivial solution, right? I don't want the trivial solution. It is true. 0, 0 will also be, correct. But that's not what we are talking about. So, okay, so here is 2 minus, what I will do? I will do like this. Let's see. More accurate, let's see. I don't know whether that is an issue, but I'll see with this. Okay. A is defined as B minus Eigen dollar values. Okay. Eigen dollar values times, right? So percent time percent I. Are you with me? Eigen, what is that? Eigen dollar. So I have to store that first. I haven't done that yet fully. Okay, let me store that. E is equal to Eigen B, and then we are talking about E. Okay, A minus E dollar values. Okay, that is now good. Percent multiplication percent I. Okay, identity matrix. Joy. I have to do that. So why don't I do that this way? Otherwise, I have to define I matrix also now. Okay, I is equal to matrix.
1 0
It's 1, yeah, 1
0.
0 0 1. Are you with me?
Yes.
Correct? Oh no, I have to do that. C, that defined by row, 2, and row. Go to 2. Okay. That's fine. Now I define a. What am I trying to do? I have to define a new matrix and then solve. Okay, so that I'm doing all these things so that I don't lose. I don't think it is a rounding error, but there is something going on. I have to explain. I'll do that. A minus E E dollar. These are all, it's clear to you, right?
Yeah.
Percent I.
I mean, that should return 0, right?
Solve. Yes, what is that? I'm sorry.
I mean, this is
You want to
okay.
see what it is? This
Yeah.
one. This is what, I'm glad we checked it out. It says non-conformable arrays. Why is that? We know E is eigen, right? So dollar values. So this is good. I see.
Is it a array or the list representation? This one.
No, that's okay. So what happens is that I can't do this. This is not a matrix. That's what it is. Okay, okay. Got it. So I values times I. Yeah, that is working all right. I should not do percent star percent because E values are not, is not a matrix. Are you with me now?
Yeah.
Okay. Yes. E dollar value times I. This is this is what you are trying to solve. Okay. Right? Solve.
Yeah.
We're going to do this. Solve A minus E dollar values comma C. Remember I did that.
Yeah.
Star. I put star.
Yeah. Started. Yeah.
Yeah, it shows
That's the same.
0. Zero is a trivial value. But
Okay.
we got this answer. You remember, eigenvalues is the eigenvectors is this. You remember, no?
Yeah.
So 0 is a trivial one. We are not talking about trivial ones here. So I'll have to get back to you on this one. Okay.
Okay. Sure. Yeah.
It
Yeah,
just
but I understood the earlier part of how
yeah,
you
I would
derived the lambda.
encourage you to
Yeah.
think in these lines. That's all. Okay.
Yeah.
Yeah, I understood that. Okay. So it should come out with we kind of went through in the direction of it's all solving equations, so this should this is how it is going to do that and so on. Okay. So I have to I made that comment, so I will come back to you on that one. Is that okay? So
Yes.
take a 5 minutes break
Yeah.
and we come back and continue on this one. We have got some fascinating things already. This hour was very, very productive in my opinion, because I was able to very nicely get you to that understanding of what's going on with the Eigen system and how it's connected to these the transformation matrices, which are A matrices, and A matrices could be very general, new coordinate system, all those things. Okay, so we have done very. I feel nice that there is something deeper is going on and you are able to get it. Okay,
Yeah.
this one.
Sure. Yeah.
Come back in 5 minutes. Thank you.
Yes. Thank you. Bye. I am back.
Okay, welcome. Thank you. All right, welcome. Thank you very much. Okay, so right. So I want to go to this particular, example again, because this explanation is given here. It's the same thing, okay? So are you seeing here?
I'm not seeing the screen.
Not yet. Okay, I'm sorry.
Yeah.
Share screen. All right. I didn't stop the recording, so here it is. So in the example, if I do the same thing, you are going to get 0. Why is that? Because for example, in this case, the example is 8 minus 2 minus 2 5. Okay, and exactly like I solved it, it is given here, but for a different matrix. So I have an equation in lambda, which is a quadratic equation. I got 9 and 4. Okay, the eigenvalues are 9 and 4. Are you with me? And so you substitute that 9 take the first 9 and substitute that. You get minus 1, minus 2, minus 2, minus 4. With me?
Yeah. Yeah.
The resulting equation is this.
Yeah.
Okay. So all right. Now, first of all, this is this equation is equal to 0. That means we also said that the determinant has to be equal to 0.
Correct.
Right? So determinant is equal to 0 means it is what is called that there is dependency in the equations.
Right. Yeah. Yeah.
Super. Okay, there is dependency in the equation. So what we have 2 equations and 2 unknowns, and they are basically one is dependent on the other one in terms of those row operations, right?
Correct. Yeah.
Now, so that means if you have a solution, you can take the lambda is equal to 9 as a solution, right? Now, if you take a solution, how do I say this? You just pick any vector, any value for V1 and calculate what V2 should be. So I'm saying here, because of the dependency, you take any value. One you can determine any random, it's okay. That's what dependency means. Because you can only determine only one variable. You cannot determine the other one is automatically dependent on the first one. That's the point. Okay.
Yeah.
So you take any number, then you get the corresponding the V2 value in this case, right? So in this case, I'm saying he is saying for the 9, because we started this equation is starting with the 9, right? This equation is about starting with the lambda is equal to 9. That's the first eigenvalue, right?
Yeah.
This equation is specifically for lambda is equal to 9. And what the logic I'm going to tell you, it happens for lambda is equal to the other value is lambda is equal to 4 also. So let's keep this 4 separately. I said for the lambda equal to 9, these are the equations and they are dependent equations. That means both of them are not independent. You won't get x1, v1 and v2 separately. Okay. You can, once you determine v1, automatically v2 is determined. That's what this equation means. So you say v1 is 2, then v2 becomes 1 in this case. Are you with me?
Yes. Yeah.
That's it. Your system is determined. With the one direction, for the lambda is equal to 9, you have determined the direction of the vector.
Okay.
And it can be any other value also, remember that. It has to satisfy this condition, that's all. In other words, lambda equal to 10, v1 is equal to 10. You can do that. If you do that, v1 equal to 10, what is v2? 5.
Yeah. Yeah. So lambda is a scaling factor, right? And v1 and v2 are
the direction determining values.
Right. Okay.
Direction determining values. So that's why it's a vector. V1, V2 together.
Okay.
The vector which determines the direction. And lambda tells what scale you have to use for that direction.
Got. Okay.
Excellent. Okay. So now that I determined the vector direction for the lambda is equal to 9, I can determine the same thing. Direction for the lambda is equal to 4. That is the second value here. Second value. So you got two eigenvalues, determine the eigenvalues. Once you determine it, you solve the eigen vectors. So then you might question, so what is this one? Again, I don't know. It's just another. You can, as I said, you can fix any number. Once you fix a number, the other number is fixed. That's all my point is.
Okay, got you.
Okay.
Yeah.
So you might question, and I was only trying to think, maybe there is some relationship. See what happens. Sometimes they want the distance of the eigenvector to be unit value. That determines one way of fixing the eigenvector. Am I connecting with you?
Yeah.
Okay. So unit eigen, so they but I still want to give you back a little bit more information later. Okay.
Yeah. So that's why I was also looking to accurately identify the eigenvector from the lambda. So I mean, this equation should give you that, right? At the end.
I'm sorry, which?
This equation, like, I mean,
Yeah.
we are finally concluding that one is dependent on
that is what it is. The solution is only through the equations coming to you.
Yeah.
Absolutely. Okay. It's coming to you only through the solutions.
Yeah.
All right. Now, where am I going with this? Now, the very important part what I want to tell you is the following. That is, let me go to this very foundational principle. Okay. So, what we are saying is that for sigma by P, I have P eigenvalues and then the corresponding eigenvectors. Agreed? This is first eigenvector that corresponds to the first lambda 1 value. Okay, this is the second eigenvector that corresponds to the second eigenvalue. This is the third eigenvector that corresponds to the third eigenvalue. This is the pth eigenvector that corresponds to the pth eigenvalue.
We are also doing the transpose.
Now I'm coming.
Yeah.
So this is a fascinating statement I'm making here. In other words, your variance covariance can be decomposed into P components. That is, decomposed means what? It's a sum of writing. If you have variance covariance matrix, which is about the total variance in the data, I can say this is one part of the variance. Pulled out of that total variance, I'm saying this is one part of the variance. This is the second part of the variance. The third part of the variance. This is the pth part of the variance. You sum all these things, you get the sigma.
Okay.
And that is what this statement is. But epsilon, this is I'm calling it as epsilon is your first eigenvector. You use the transpose of that, then it is a matrix. This is P by 1, this is 1 by P, so this becomes matrix, right?
Yeah.
And then I scale the matrix by lambda 1. This is a matrix. And then I scale that lambda, that matrix by lambda 2. And that's what I'm doing here. When I sum all these things, it will automatically get you this exactly same. That's what this statement is saying. So that is called decomposition. So I'm saying sigma is decomposed as a sum of individual access contribution. This is the first access contribution to the variance. This is the second access contribution to the variance. This is the third access contribution to the variance, and so on. Right? So I am able to decompose the total variance in a fairly interesting way. What is the advantage? What is the advantage? I am able to rewrite the total variance in the new coordinate system. Okay. And interestingly, I can rearrange where the maximum contribution is coming, because lambda is all of them are positive. The highest one will be having the maximum contribution in that direction, because these are all perpendicular directions, right? Lambda epsilon 1 is one direction, epsilon 2 is another direction. These are perpendicular. It has to be perpendicular, right? The new coordinate system should also be perpendicular. X1, the original XYZ are perpendicular, right?
Yeah.
Likewise, the new coordinate system should also be perpendicular. That's why it will become a perpendicular, right? It will become a coordinate system.
Yeah.
Okay. So the mathematics will arrange the lambda ones in such a way that lambda 1 is the maximum value, lambda 2 is the next maximum value, lambda 3 is next maximum value, lambda p is the least value. It will arrange it like that and give it to you. Advantages, I know which direction has the maximum variance from the sigma.
Oh, okay.
That's beautiful, isn't it?
Yeah.
Because remember, our problem is always explaining variance.
Yeah.
Explaining variance. In this case, I don't have a dependent variable, but I just have the whole blob of coordinate values. So, important problem to solve is which direction has the maximum variance. And that's it. Your problem is solved with the eigenvalue system. And within the eigenvalue system, PCA arranges the eigenvalues, scaling, so that the first one is the highest value, variance explained direction. Second direction is the next highest value, highest variance explained direction.
Yeah. Right.
And so what is the advantage in this? If the 95% of them, 90% of them, 80% of them are explained by first 2 or 3 dimensions, why do I care about the rest of them? I don't care.
That's right. Yeah.
It could be a huge data set, huge big data, it doesn't matter. So this is a way of reducing the variance to most essential dimensions. Not reducing the variance, explaining the variance to most essential dimensions.
And reducing the number of variables. Dimensions.
Let's call this number of dimensions. Because in the new coordinate system, we don't know what the variable name is, but it's a linear combination of this previous coordinate vectors, isn't it? Directions, isn't it?
Yeah.
So it helps us to reduce the number of variables, and at the same time it helps us to maximize the explainability of the variance. Isn't it beautiful? That's what this is. This is called PCA, Principal Component Analysis. Main component analysis. Main directions where most variances are explained. In the total variance case, I can't say variance, it is really total variance, because there are so many directions are there, so many variables are there. So that's it. So the software PCA gives us our answers, all those things. We are ready to solve the problems. Are you with me now?
Yeah. So question on this, these transformed coordinate system, right? So that is in a way expressed as a lambda times proportional to the source coordinates.
Lambda times the new directions.
Yeah. Yeah.
Lambda is the scaling factor for that direction.
Yeah. Yeah. So, but if you are relating from the source points, right? The source, data that we have put that into the matrix form. So is that
not the source data? Remember, no, we are starting with the variance covariance matrix.
Yes.
So
yeah. Oh, yeah.
Variance covariance matrix.
Right. Okay. So my question is, okay, with respect to the variance, the source variance covariance matrix, we have computed the eigenvectors, right? So would the proportionality still maintained? Like suppose the covariance is 0.7 and the corresponding eigenvector is also proportionally related to the 0.7 value, or it gets distorted?
No, it will. It is a different, in the new coordinate system, the whole purpose is, and not only that, we are kind of rearranging. See, it's all linear combinations now, right?
Yeah.
In the new coordinate system, linear combination of original variables.
Yeah.
But the benefit is also we are doing the mathematics to rearrange the coordinates so that the first direction, we want the first direction where the one which explains the maximum variance.
Okay. Yeah.
In the maximum total variance that we are talking about.
Yeah.
So it will not be connected, their point, variance is, 0.7 or 70, is it going to be, some constant value of the 70? No.
Okay.
Okay.
Yeah.
So let's do some example, then it will become more clear, I feel. Okay.
Sure.
So read all these notes. I'm not going to go through this. I think I have passed the most essential things to you. Okay, and through you to Patro also. I hope. Okay. Did we by any chance mistook what Patro was saying? Because why Patro didn't come through, I don't know. I don't know. Can you send a message to him if you don't mind? Or I can also send a message give me just a 30 seconds. I mean, of course, it's going to be over in another 30 minutes, but nonetheless, okay. So let me, I just want to just let's get my shirt off. It's cold, very cold. I'm using the phone to connect to Blue Jeans, so I was searching for that. Oh, Lord. I should do that. One moment, please. Just leave a message for him, okay? I'm kind of. Oh, I see. He's taking the. No, he didn't say time of iPad Pro. I don't see anywhere, Patro saying I can't come. Okay. So I'm going to send this message that we are missing it. All right. Are you with me? Are you able to hear me? Hello?
I'm on mute. I can hear you. Sorry.
Okay. That's all right. Okay. Thank you. So, so let's go and do some. So here is now you may be able to make sense here. So the original coordinate system is this x, y, z, right?
Mm-hmm.
So this is your new coordinate system. Your axis, the first major axis is this.
Yeah.
Second major axis is this direction. It
Yeah.
should be perpendicular to this, right? It will be perpendicular. The mathematics works it out. So once I determine this axis, I know what this axis direction will be, right? That is the second eigenvector anyway. And I also know the third eigenvector direction is this one. Are you with me? So this is a 3-dimensional, also 3-dimensional. But this is your coordinate system. So your first eigenvector is pointing out this direction. Second eigenvector is pointing out this direction. Third eigenvector is pointing out this direction. So each one is an eigenvector. Are you with me?
Yeah. Yeah. I got it now.
Go and do some work. Okay.
And we'll be choosing the one which is having the maximum variance there, right?
It will automatically come. The first one is the maximum variance.
Maximum, yeah.
Planing direction. Okay. So I'm going to move on this example. Leave it, and I taught you this one how to calculate the standard. So if you standardize the variable, you are standardizing like this, right? If you do this, it's basically it will come back to your correlation matrix. You agree with me?
Yes, correct.
Super.
Correlation.
Very
Yeah.
nice. Very nice. That's another way of saying it. So let's take this example. Okay. So this example, I will show it to you in page not found. So that's okay. Don't worry about it. I think also I learned it improves visualization of PCA and PS. Okay, so tour package has this data. This data is about 300 and odd. So let's go back to this 300 and odd towns in USA, and they are ranked on 1, 2, 3, 4, 5, 6, 7, 8, 9 characteristics. They are ranked for the livability of those towns. Okay, so shall we do that example?
Sure.
Package, library, maybe, I don't know whether this tool is there or not. Let's see.
So I have a question while you're doing this. So this principal component analysis, this is a approach to find the most deterministic, I think I'm missing the words, but you'll be reducing the dimensionality, right? And you will have
use the dimensions of the big data.
Yeah. After that, right? Once it is dimensions are reduced and we have a condensed set of data points, right?
Yeah.
In terms of eigenvectors.
Yes.
So we'll be putting them into the model, right? Appropriate model.
No, that is one of the applications. There are lots of applications for this. You can say you can reduce the big data on the independent variables, reduce it to most essential dimension, put it in the model. You can do that. You can use it for analyzing NLP. You can use it for analyzing images. The images can be just compressed into few dimensions rather than 100 plus dimensions. Okay.
Yeah, okay.
Similar ideas. Okay, we are going to talk about all those things. Okay?
Yeah, so it doesn't tie to a certain kind of models, right? It's open for anything that you want.
Because we are talking about the X vector reduction on the X vector side.
Yeah.
Reduction on the X vector side. X could be just could be called as independent variables collection, or it could be just blob of variables where we are talking about clusters. We are talking about other things, which is unsupervised method.
Okay.
So I loaded the library tool, TOURR, and it has the data set called places. You can if I just call, I don't even have to do this, play data, places, all those things. Just put, head places, right? Because it is already there. See, this is what the data is. Are you with me?
Yeah.
So it has climate condition, right? Climate and terrain condition. There is a score people give, right? And these are just those scores. Housing cost. This could be just housing cost, actual dollars. Okay. Healthcare score, crime level, transportation, education, arts, recreation, economics. Then case number. Also has longitude, latitude, population size, and state number. Okay. So if you look at this, length and row of places, we have 329 places for which we have this data. So far, so good?
Yeah, so it doesn't tell the name of the place, but it goes by the climate ID.
Yeah, it doesn't give. This is just data used for data analysis. So those are all given in case number 1, 2, 3, up to 320.
Yeah.
It doesn't say the name. The original data has it. It is taken from Places Rated Almanac. There's a book called Places Rated Almanac that they publish every year. If some year they took it. Okay, so we want to go back and check. Places Rated Almanac. You see this one, 2021? Data R. This is 2021. American for the arts. Okay, they also have this data. So here is the data. right? National Arts Administration. So they are interested, and they research website Places Rated Almanac, your guide to finding the best places to live in America. Okay, 343. I don't know. I don't know what number I was telling you, but you can see the data here also.
Yeah.
With
Okay.
me?
Yeah.
Oh. Huh?
Yeah, I'm there.
Okay, good. So every year they do it. Okay, but this is just for some year. Now, these are the variables, but you'll be surprised. They're all correlated. They're all related. So you don't need all the 9 dimensions.
Correct. Yeah.
So remember, you can do variance. You can do PCA for sigma, or you can do PCA for correlation also. Because if you standardize the variable, it becomes a correlation matrix actually.
Correlation.
Right?
Yeah.
Variance correlation matrix is same as correlation matrix if you standardize the variable. So there's the fluffy stuff is there. Okay, it's either way you can do. You don't. We are talking about explaining the correlation or explaining the variance. It doesn't matter. Same thing. That's what our fundamental problem is, isn't it? Okay. So we have the data here. Just we have to do the analysis. So I think there is a command. Simply you can use it. PR. Or there are many packages that you can write your own package now. Because it's all about eigenvalues. It's nothing to do with special special codes. It's just about eigenvalues and eigenvectors, isn't it?
Yeah.
So simple, right? That's why you'll see everybody will write their own PCA. But you have to do a lot of other additional things now, how to test it, all those things. So if you want, you can write. That's my point. Okay. So there's something called stats package has PR comp. Stats package also has print comp. Factometer, there's another package that has PCA. There's a package called ADE4, AMAP, all these things. They are all talking about PCA.
What are the base packages for the CRAN then? So all are supported by the CRAN?
These are stats is part of the base package.
Okay.
See that one. If I say PRCOM, it should work. Okay, let's go there. Right, PRCOM. Okay, so let's do this one. PRCOM. See there, it's part of the stats package, it's base package. Okay. I don't have to load in. PRCOM, you just have to put the name places. But remember, I don't want to put the place, I need to remove all these things. Case number, longitude, latitude, path, state number, all this. I need only this first line. Are you with me?
Yeah.
So I want to take only from 1 to 9, comma, nothing else. Only 9 columns.
No, include everything, right? I mean, usual.
No, I don't want case number. I shouldn't use it, isn't it? Should I use case number?
No, yeah, it doesn't tell anything about the data. Yes, you don't need case number.
Latitude, if you want to use it, you can use it. But I'm just telling you, do you want to use it?
Okay. Yeah.
No, you don't need to do that. It's because it's a place, it's location. And again, maybe population you can use it. I agree with you. But just let's work with 1 to 9. It's easy to use. State number do you need to use? No. State number you don't need to use. We want factors coming together to explain the value of the place.
So if we start using this, right, I think the model can go, can predict something differently, right? Because of the case number, it is increasing. It might,
you should not use case numbers, period. It doesn't have meaning.
Correct, yeah.
You should not use state number. It doesn't have any meaning.
Meaning, true, yeah.
Perhaps population might mean something in association with, because the more the number of population, perhaps the more facilities are there. I don't know, right?
Yeah.
And that is correlated with these things. But not all there is. Typically, longitude latitude should not be used also. But I would not. Again, the combination of longitude latitude is somehow related to all this goodness of this variable. You can go ahead and use it. For example, all northeast states have some, they're high quality life compared to Midwest. Okay, or also California is a high quality life compared to Midwest. So there seems to be some, if you think that it matters, you can throw it. It doesn't matter, right? But definitely case number doesn't make sense, and state number also doesn't make sense. But I'm going to use only the first 9. That's what people use. Okay?
Yeah.
Are you with me?
Yeah. Yeah.
So, and then we want to, standardize. Why do we want to standardize? Scale is equal to true, you have to say, okay? Standardization will remove, okay, the differences in it will remove the differences in unit of measurement. Okay,
Right.
but here there is no unit of measurement need to be removed here. Remember that, okay? Because it's just a score, same score. People are scoring, giving some numbers on some standard scale. They are giving some numbers. We don't need to, standardize, but we'll put the standardization equal to true. Okay, that's what it is, right? Are you with me?
Yeah.
So here is basically I got this, print com, PR com, because your lambdas are, the standard deviations. I told you, the variance, right? Yeah, it's a scale, right? Because it's a scale, I want to say it's a standard deviation. I said it's a scale, right? Remember that? So the better terminology is standard deviation, not variance, right? So the lambdas are the eigenvalues are your standard deviation of that direction. Each of the eigenvector direction, why it disappears.
Okay. Okay. The values are the standard deviations. Okay.
The lambdas are the standard deviation. Okay, and these are the vector direction. PC1 column, PC2, PC3 line. These are the vector directions. These are the eigenvectors, vector directions. Are you with me now? And you can see these are all arranged in the decreasing order. That is the beauty.
Yeah.
And this is the least value. Last eigenvector refers to, that is the 9th eigenvector here. 9th eigenvector doesn't mean the 9th variable. It's a combination of weights you give for all these variables. Excuse me. Sorry. Okay. So the 9th eigenvector direction has the least importance, 0.3469. On the other hand, this has 1.84. So between the last and the first, how many differential is there? 1.84 divided by 0.39, right? It is almost 5 times it is explaining the comparison, right? So why do I care about this one? These things matter.
Yeah.
So it may be
is 1.8. Okay, it's a standard deviation. Okay, I got it. It is not the percentage, right? Yeah.
Huh?
It's a standard deviation unit, not the percentage of the variance explained.
But you have to multiply. You have to square it to get a percentage of variance. But if you start percentage of variance, right? The moment you wrote variance, you have to square them.
Correct.
So square this divided by sum of all these things. So
yeah, I think I got it. Yeah.
Okay.
Oh, yeah.
So you got the directions. So you just use only this first 2, for example. In a 2-dimensional rotation, you can see the big data summarized into the most essential dimension and look at it, how they are located in the 2-dimension. Or in the 3-dimension. At most in 3-dimension, you can see them. What is 100-dimensional data? You can see them in 3 dimensions. Okay, that's what the beauty of this one is. All right.
Yeah.
So
and now we will use the PC1, PC2, and PC3 values for regression models, right? Or any other model.
You can use it. Yes. If you want, if it is a regression model, if you are trying to build a regression model where you know y, we don't right now. I don't have y. Do I have y?
No.
Agree? I don't have. I don't know why.
Yeah.
So right now I'm just interested in reducing the dimension and interpret it. So I may end up giving interpretation for all these things. What is this one? This one is maximum is housing cost. It talks about housing cost. It is talking about healthcare. Okay. It is talking about transportation. It is talking about arts. In fact, this is the only place arts is valued so high. Look at this one positively.
Yeah, others are negative.
So, well, there is the last one is also valued at 0.68 highly. So maybe,
Yeah.
the last dimension that matters to people is, the arts really, in the ranking. That's how I interpret it. Okay. But if you want arts to be good and along with some other factors, and we want to be valued very high, then you say, the first dimension, arts also values. In fact, arts and is same as valued as the healthcare is. So
Yeah.
these are probably the people. These are the towns where it's good. It's kind of metropolitan, and also people who care for healthcare.
Yeah.
So now we start interpreting these principal directions, which are very hard, but that's where you get the insights. Insight. This is what insight is about. It tells you, right? It looks like urban. For example, urban places where arts and healthcare are valued. The PC2 is not urban. Remember, it is not, at least it's not valued at all. In fact, probably it's one of the lowest valued for healthcare, and also low valued for education and arts. But they value for recreation and economy. In fact, economy is the highest value, right? So I would say these are probably newly growing places where arts hasn't taken root yet. Okay? So, arts hasn't taken root here. Also, healthcare hasn't taken root here. So it's probably new towns, newly growing towns where economy is thriving, matters. So if you go back to the data, you can actually locate these kinds of things. Is this urban? The places where it is valued high. Is this an urban, well-established towns?
Mm.
The education is there, arts is there. Well-established towns don't have to be economically sound, though. Remember, because they get money from the government. But healthcare is very good, and arts is very good, which is a sign of an urban development area. So you have to interpret things like this, where the high values are loaded, low values are loaded. Based on that, you can interpret the locations. Are you with me?
Yeah. Yeah. So can we plot this visually? Is
Yes,
that simple?
absolutely. We haven't gone there yet. We are coming. Yes.
Yeah.
So you cannot visually plot these 9 dimensions. Remember, right?
Yeah.
The whole purpose is to reduce it to essential dimensions
Mhm.
and then visualize them. So we are going to do that one. Okay, give me a moment.
Yeah.
So I'm going to take this command. Okay. Yeah. Let's do this one, visualization for the this places are rated almanac. Okay, problem. They have done it for crimes, or we can just do the crimes data. Another analysis also we can do that is a crimes data. Okay. So, what happened? I closed everything. Maybe that's what it is. No, yeah. Let's see. It's a not tool package. Yeah. Was it a tool package analysis? PCA RS analysis R. So surprisingly, it takes so long. I don't know why it takes so long. Okay, I have to do like this, page down, page down. Okay. So, are you looking at this screen now?
Yeah.
So there is also another data set called USARS. Okay,
Mm-hmm.
USRS.
Yeah.
So when you look at the USRS, there are obviously it's by state, so there is going to be 50 values and so on. So on the R side, let me show you a little bit before I go to that screen. Okay. Head USA. Yeah, it is already there, loaded. Okay. That's what it is. So if you do the end row, there are 50 states, so we have 50 rows of data, which are 4 of them are there. The kind of percentage of arrests made for murder, assault, not percentage. I think assault is a count or some kind of a number. Let's say I have to go back to that. Okay, I'll come to that. Urban population, great. Okay, so let me question this, and it will give me some information about health file. So, this is arrest per 100,000 residents for each of the 3 crimes. These are arrests for 100,000 residents for each of the 3 crimes: assault, murder, and rape. And then the fourth one is the third column, is about the urban population percentage. That is, Alabama has 58% urban population percentage. Okay, for 100,000 people, there are 236 assaults are there.
Yeah.
There are 13 people are getting murdered, and rape is 21% is getting raped. It's pretty bad. Sorry about that. Man, I don't like it. What am I going through, right? Okay, so that's what it is for every state we have that. Okay, but possibly there are only 2 dimensions. They are already 4 dimensions is showing us, right? Perhaps only 2 dimensions. Let us see what it is. Okay. So let's just ask for summary, and it gives you all these minimum, maximum, all those things. Okay, fine. But I can also do the variance. Using the apply function. Variance. This is just gives you apply. Second means by column. USRS, 2 means column, and what kind of a function you want to apply its variance. Okay. So this is, if I do the variance covariance matrix for this will be the diagonal values. Agreed? Okay. Page down. The PR comp, USARS scale equal to true. Are you with me? That's, I take it and PR out.
Yeah.
Maybe I'll make it a little bit bigger, more bigger. Okay. And the names, I just want to find out. So I store the data into PR out, and then I just want to know what they are. Okay. And they have some names, which is, so the names are standard deviation, rotation, center, scale, and X. These are the things that are stored there in the PR out. Rotation is same as the factor loads. That is what the principal component to the values are. You remember, right? Those are the direction where the maximum variance is explained. Next one is the perpendicular to that. That is the direction by which the next maximum variance is explained, and so on. Okay? And they are stored in X. So if I want, the factor score, I have to go to the X. Okay? Standard deviation is, the usual way we define. Now, rotation, so here is the, basically the principal component values, right? PC1, PC2 gives you the rotation, okay, by the variables. That is our principal component rotation. In this angle, this is one of the direction, this is the next direction perpendicular to this. This is another direction perpendicular to this. This is another direction perpendicular to this. Are you with me?
Yeah.
Okay. So the first one is it loads on murder. Okay, it loads high on murder because nowhere else is high. It loads on assault, and it also loads on rape. Murder, assault, rape. It has a high, weights for those values. So it could be. Basically, this is this is about basically how wherever we get high scores for the states, it tells you this is basically a general measure of crime. More crime is happening there. Are you with me? Because all of them are about crime, and everything is loaded in the first dimension itself. If you look at the second direction or dimension, it is, second least loaded on the model, but it is, it is highly urbanized. Okay, it's also least load, the lowest loaded in the assault side. There are not much assaults, but there is some rape is there, and it's also, one of the least murders happening. The least murder happening is the fourth dimension. If you want to interpret the dimensions in the new, coordinate space, you have to use these ideas. So what we are saying,
can I ask a question here? So for the PC2, right? It shows a negative direction for the murder, right? Minus 0.1. So
where is minus 0.1? You mean minus
0.41? Minus 0.4. So in terms of the magnitude, right? It is very less. But in terms of it is pretty significant that it is very less.
It is the second. The states which are the states which are scoring less on murder.
Yeah.
Yeah, those are the states. Yes, got it.
So the variable is significant, right? My question is.
The variable. Okay. That's a very good question.
Because it is
the variable
trending to negative.
To your lambda values. Remember that. Because the more the lambda values, the more significant.
Correct. So
there is
in this case it is negative, right? Is it significant or it can be ignored?
Yeah, it is significant in the negative direction.
Negative direction, absolutely, that's where I am coming there.
Yes, exactly. So let's continue to go. The PC1 is about crime. If I have to say, direction. See, this is giving you some meaning, right? Murder, assault, urban population, rape, and similarly, I should give you the meaning for these things also. So what I am saying is, PC1 is about crime level. Okay. PC2 is about urbanization level. So these are not that urban. These are highly urbanized. Do you see this one? This is not that urbanized. This is medium urbanized. These two are medium urbanized. So second is all about urbanization. The first is all about general measure of crime. So you have to think about what kind of interpretation you can give for the new directions identified in the new coordinate system. You need that thinking. The success of PCA is only when you interpret it in business sense, in day-to-day life sense. Okay? Think about that always. This is a very small problem, toy problem, but it gives those ideas for you. Now, you can take this PC1 and PC2, right? This PC1. Take this PC1 vector, okay, and PC2 vector. That means if you take only PC1, PC2, you have only two dimensions. You have two points that determines in a two-dimensional plane, correct?
Yeah.
If you consider only PC1 one direction, PC2 another direction, you plot these 2 points in a plane. And plot these 2 points, in the plane and identify what that value is, okay? So what I'm saying is, I have PC1 here, let me see. Okay, that's better, right? Okay. So what we are saying is that, I have PC1 in this direction and PC2 in this direction. I plot all those points, the values using those PC1 and PC2 for each of the state. Okay? And if you look at this one, there is a meaning going on here. If you can see, you have some, you can see internally, you can validate it. This is the point New Jersey, whatever New Jersey gets PC1 value is very close to 0, PC2 value is around 1.5. That's why, New Jersey gets here. South Carolina gets here. PC1 value is around 1, PC2 value is -2. So this is urbanization, remember that. Urbanization, this is at the crime level. So if you look at the least crime level, Vermont, Least crime level is the left side. Okay, high crime level is right side. Vermont, West Virginia, South Dakota, New Hampshire. These are all least crime level. Do you agree with me? On the left side, does it make sense?
Yeah.
On the other hand, high crime levels are Florida, Nevada, California, Michigan, New Mexico, Maryland. Okay, all this in broadly speaking, high crime level, right? On the other hand, the urbanization is Hawaii, New Jersey, California, Washington, Connecticut, Rhode Island. These are all highly urbanized, right? The least urbanized is North Carolina, Mississippi, Arkansas, Kentucky, West Virginia. These are this way. Reading is urbanization. Are you with me?
Yeah.
So this is how you interpret it in a two-dimensional, reduced dimensions graphical approach. And it is very difficult to get that graph. Basically, you say by plot. This is a special type of plot. We are plotting the Eigen directions values. That is called by plot. We take only two dimensions, two principal components.
Yeah.
So you can actually do three principal components and do triplot if you want. And that is what t-SNE is all about. There is something called t-SNE. I will talk to you later. Okay, T standardized, Eigen directions. Okay, and this is a biplot, and of course I told you can do a triplot, which uses the three most important principal component directions. So this is useful, and if you bring the four directions, you can see in this direction is all about urban population. Actually, even though I put PC1, PC2 only, you can see based on this towns here, California is here, New Jersey is here, Texas, not Texas, New York is here, Illinois is here. Based on that, you can see that direction of this is urban population, right? So based on the kinds of rape, and those are all based on high values where you have. You go back to the data and bring back this kind of ideas. Okay, interpret these kind of things. So this is how you do your PCA analysis. This is how you get the understanding about the principal components, their plot, interpretation.
Yeah, I think the overall summary is, it's a very effective way to reduce the dimensions of the input variables, and I think this is probably like some input. We are talking about a few columns, but in some realistic data sets it could be thousands of columns, right?
Yes. Okay, but we are going to see something, many examples, many interesting examples. Okay, so we can do the same thing, the same command, you use it for the previous data, the houses, so we can do that. Let's just, finish our session with that. How about that, okay?
Sure.
So I just need to do, store it in PR out, and then rotation, just ask for rotation, and then just do PR out by plot. Okay. Are you with me?
Yep.
PR out is equal to PR comp. Okay. Data is USA, not USRS. We are talking about places, not places, but we want places. Yeah, let's do the places, but only 1 to 9 columns. Okay, scale is equal to true. And PR out, names PR out, right? We will want to see one more time. Recall this. You got it here.
PR out.
Rotation.
Rotation.
Right? PR out, dollar rotation. These are your eigenvector directions, principal component directions. We are interested only, but when you do the by plot, automatically it will come. Okay, all these things. automatically. Okay, so by plot here out comma here equal to let's see zoom because it has a lot of values, no? So it might be confusing looking. That's all. But let's do this. So we don't have the names here. Yeah, if you have names instead of the numbers, ID numbers, you will have the the place that will be easier to read through. Okay. So there are only small negative values. That's why it is here. Most of them are in this range. PC1 is almost between -2 to 5. PC1 is almost between -2 to 5. PC2 is almost between -0.5 to 5. Values. So most of them are here. So I think it's the better, if you can put the names of the cities, then maybe you can make sense, because I can make sense, based on my experience about USA places. You may not, perhaps, you are getting to know the places, perhaps. I don't know. How long you been here?
Been here for almost 7 years. Yeah.
6 to 7 years. Okay. So you may also know. So that's how it is. It is done. We do the analysis.
What about this axis on the right? The perpendicular axis is
This one?
-0.5, 0.0.
Oh,
No, not here.
I see.
Plot. On the plot, 0.5, 1.
Okay. So
And on the top as well, top horizontal.
yeah, top as well. Near the top as well. Let me see this one. That's very interesting. We did here. That happens here also. Okay. Urban population here -0.5. Here also -0.5 to 0.5. PC1 is direction 0 to 3. Yeah, I'd like to look into that one also. Okay, let me get back to you on this one. Okay.
There's some kind of a scale.
Yeah, but then I click on it. It gives me this very interesting customizing the biplot. You can even, if you want, you can do specifically, right? Specific range of x values and y values also, so that it is concentrating only on some areas.
Yeah.
The biplot has that facility for you. Okay. So biplot is giving you the PR out, the x values. Okay.
What are x values here?
And it is taking only certain states. Okay.
Okay.
So x values refers to your data. I think. Back to that. One second.
Original data, you mean?
Yeah. Let me see that. X refers to the factor scores. Okay.
Okay.
Let me go back to this, or not this side. Okay. So let's see, head X. Well, wait a minute. I said names.
PR.out.
So echo $X.
Yeah.
Okay. X. So it is referring to this is 9 principal components, right? 9 principal components we are talking about. Oh, it's only we are talking about, okay. X values are, if I put that, PR dot out, $x, the whole vector will come. You see this one? I can't even give you more than 111 because max out. So it is the X refers to the eigenvector dimension on the on eigenvector dimensions, eigenvector values on the whole list of places. Okay. Rotation, PR out,